Hi, in this video we will discuss about derivation of shape function for one-dimensional linear bar element. So let us consider a one-dimensional linear bar element. So this is our one-dimensional linear bar element. So there will be two nodes. So node 1 and node 2. Let L be the length of the element. So let L be the length of the element, and let us assume an axis system. Say only one axis. There is going to be only x axis. Since we are dealing with one-dimensional member, there is going to be only one axis x, and here it is x is equal to 0, and here h is equal to L, and at h is equal to 0 there is going to be a displacement of nodes, say u1, and there is also a displacement of node u2. There is also displacement of node 2, that which is u2. So let us write all those things. So L is the length of the element, length of the element, and u1 and u2 are the displacement of the nodes, are the displacements of nodes 1 and 2. So our aim is to find the displacement function. Fine. So let us try to derive the shape function for this. So as the first step, what we will do is we will assume a trial solution. So we are going to assume a trial solution. Okay. The trial solution which we are going to assume is, say, u of x is equal to a naught plus a1 x. So this is a linear trial solution. We can observe it is a linear polynomial, okay, with variable x. So u of x is nothing but the displacement function which we are interested to find. So u of x is the displacement function, okay, on along x direction, along x direction. So we are dealing only in the x direction. So I am taking u of x as the displacement function along the x direction. Fine. So we have some boundary conditions also. So the boundary conditions, okay. So at h is equal to 0, at h is equal to 0, at this point, my displacement function is u1. So that is u of x is equal to u1. So u of x is equal to u1. Okay. So if I apply this boundary condition to the trial solution, let me take this trial solution as, let me name it as equation 1. So if we apply this boundary condition in equation 1, what we get, we have u1 is equal to, that is u of x, is nothing but u1 is equal to a naught plus a1 into 0. So I'm going to leave this term. So it is only u1 is equal to a naught. So let me name it as equation 2, and at h is equal to L, on the other end, our u of h is equal to u2. So u of h is equal to u2. So this gives, so if we apply this boundary condition to our trial solution, we have, say, u2 is equal to a naught plus a1 into, instead of h I have L, because h is equal to L. So this is equation 3. Okay. So from equation 2 and 3, from 2 and 3, we can try to put the equation in a matrix form as, say, u1 u2 is equal to 1 0 1 L into a naught a1. So we need to find what is this a naught a1. Okay. So before going to that, what we can do is, even we can write the trial solution also. This is the trial solution, right? We can write the trial solution also in the matrix form. So how we can write the trial solution in the matrix form is, we can write it as u of x is equal to, we can write it as 1 x into a naught a1. So let us try to find this a naught a1. So from this, what we can do is, we can take the inverse. We can find a naught a1. That is a naught a1 is equal to, I can write, if this matrix goes to the other side, it becomes inverse 1 0 1 L whole inverse u1 u2. So we need to find the inverse. So let us try to find the inverse of 1 0 1 L inverse. So we know the formula for A inverse. A inverse is equal to joint of A whole divided by determinant of A. So if we try to find what is the determinant, it is going to be L. And to find the adjoint, we need to take the cofactors. So if we take the cofactors, it will be, say, L and minus 1, minus 0, that is 0 and 1, and then we need to take the transpose of this. Finally I will have A inverse as 1 by L, so that is the 1 by the determinant, into, I have to take the transpose of this matrix, so that is L0 minus 1 and 1. So this is going to be the inverse of the matrix. So we have, so what we have is, we have 1 by L into L 0 minus 1 minus 1 1 whole inverse multiplied by u1 u2. Okay, so this is the this is the value of a naught and u1. So let me name this as, say, equation 4. Okay, so let us take now, as the final step, you apply this, applying equation 4 in, say, the equation 1. So the equation 1, this is equation 1. Okay, share that means this is the matrix form of that. Okay, so this is going to be our equation 1. Okay, I will just strike out this one, not this. This is going to be our equation 1. So applying equation 4 in 1, we have u of x is equal to 1 x into a naught a1. So we have u of x is equal to, um, say, 1 x into, instead of a naught a1, I'm going to use this. So that is 1 by L into L0 minus 1 1 a whole inverse u1 u2. So just we need to multiply it, that's all. So 1 by L uh, into, sorry, this inverse already I have taken the inverse, 1 x multiplied by L0 minus 1 and 1 into u1 and u2. Okay, so what we have is 1 by L into, so this one, it is a um, one row and two column, 1 cross 2. This is a 2 cross 2. So if I multiply, I will get 1 cross 2 matrix. So I will have, say, um, row into the first column, this first column. So if we multiply, we will have um, L minus H, L minus H, and the row into the second column will give um, only H into U1, U2. Okay, so if we take this L inside, it will be L minus H by L as the first term, and this H by L as the second term. So there are two terms in the inside the matrix. Okay, so now what we do is, as a final step, we are just trying to name this as say n1 and n2. So what I can do is I can write it as n1 n2 into u1 u2. So if we multiply it, we have n1 u1 plus n2 u2. Okay, so this n1 and n2 are the shape functions, are the shape functions of one dimensional linear bar element, linear bar element. Okay, so therefore we have u of x is equal to n1 u1 plus n2 u2. So this is our final answer. Okay, so let us apply the boundary condition again. So at h is equal to 0, what is happening? My value of n1 will be 1 and the value of n2 will be equal to 0. At h is equal to 1, sorry, at h is equal to L, my value of n1 will be 0, whereas my value of n2 is equal to 1. So what we can able to observe is like the n1 and n2 are going to vary linearly within the element. Okay, and one more point is like if you add this n1 and n2, it will be always equal to the unity. It will be equal to 1. The value of n1 and n2 at any point within the element will be equal to 1. Okay, so these are some of the like say some properties of the shift functions. Okay, fine. So in the next video we will discuss about this derivation of the stiffness matrix for this the same linear bar element. Okay, thank you.